Hello YouTube viewers, welcome to my channel Science to Technology. In today's show, Rocket Monday, we're going to talk about NASA's Punch mission. So let's dive deep into it. So this mission is polarimeter to unify the corona and heliosphere. Basically, you must have heard recently that Voyager crossed the heliosphere. Basically, it's the outer void that we are traveling through, and that has a bubble. That bubble is there because of sun, and that effect, the push-up force is the solar wind. So that jumping point is the center of the sun. Basically sun is the point, and then it goes to almost if sun is here 90 degrees from there, that's the outer edge, so to say. So this mission is specifically targeting to understand whole of it. Let there be very clear. We have a lot of mission that studied that part. We had a lot of mission that studied this part. We had a lot of mission that studied very specifically very close to the sun, but we do not have the whole picture. That's missing. So this mission is directly tailor-made to solve that issue. Basically, imagine it this way. We have early weather satellites, and these are low Earth orbit satellites. Not really that useful. The moment you put it them in geostationary, it's like, bro, tornado, typhoon, bro. So we want something like that, where it's like, whoa. So this is what we are doing now, studying the region from middle, basically exactly from the center of the sun to basically coronosphere to till heliosphere. And if you want a mathematical description of that, that is 1 astronomical unit. Basically here to here 1 astronomical unit is there. Basically slice, you can see much further than that. It's just that that's the slice they are most interested in. So that's the whole point. Heliosphere, basically they want to figure out how the heck solar wind goes from sun to the outer bubble of our solar system, how the heck that happens. So heliospheric bubble, and it's supposed to do this with 4 small satellites. None of them are big puppies, they are small sats, 4 of them. And to understand that, and the core point is these 4 are not 4 independent satellites, they are part of a whole. Basically they're going to act as a collage making machine, meaning you can't remove any one of them, it will malfunction. So fundamentally they have to give us a full picture that we could not have gotten any other way. And again, I have to say, whoever came up with their mission patch, they kind of went a bit crazy. So that's the whole point. It's collage view, holistically analysis. That's the whole point. That's why we are putting so much effort into it. These 4 puppies, it's just that give us the full picture, not just like, oh, we have this slice. It's almost like if you had a bucket and you directly scooped up ocean, you will not see any whales in it. To see the whale, you have to survey the whole goddamn ocean. Same thing. So we need a collage. Now this mission is rather low cost, that's why it's not so much splash about it. It's 165 million. Again, from NASA's point of view, that's free, and it's led by Craig, this gentleman. I have linked a very amazing, very in-depth discussion, which is 1.5 hours, but he goes deep. Specifically, I'm not happy that he did not went too deep into the polarization aspect of it, but he did went deep into the mathematics, how the heck they're removing stars from the background. But it was mind-bogglingly awesome. And it's from SWRI research institution, is footing the bill, so to say. So this is the mission that we have launched, and basically the idea is to get a full picture. Basically we are stepping up from low Earth orbit to geostationary. Same for this. Now, how we are propulsing this puppy? Well, this was launched on 12 March 2025. So it's done, it's already there, and you're like, okay, what the hell is that bucket? That bucket is SphereX. I've already made a video about that. So that's a different kind of mission. So on bottom, on the basically launch adapter, so to say, there is these tiny 4 puppies. Those 4 puppies are these. So this was launched, and it's a sun synchronous orbit, which again, it has to study the sun, so it will pay a lot in order to make sure that they are observing the sun 24/7, and they are achieving that in sun synchronous low Earth orbit. And satellites have what we call water thrusters. Yes, they have water thrusters because while hydrogen and other monopropellants or even some bipropellants would be better, they would be ludicrously expensive, and because of the hazard, idiotically expensive, meaning the chemistry itself is expensive, and the people needed and qualification and certification, all of that adds up too much, and they wanted to make sure this is cheap. So water thrusters are cheap, and again, they do not need a lot of oomph here. Like they can work with only 2 functioning. Basically, if 4 of them are drifting, if 2 of them have active correction, it will be fine. It will be like, we got this. So that's why, like, they have enough redundancy and they do not need a lot of oomph to do that. And they also have basically with reaction wheel, they also have magnetometers, basically electromagnet that reacts to Earth's magnetic field. So these are the propulsion part of it. Nothing fancy, it's just small, efficient stuff. Now, the whole reason why the whole world is excited about it, basically the people who understand how important this is because of this field of view. Basically, this is an image from his presentation. Is like, imagine sun, imagine a solar eclipse, Imagine that point. Now imagine how big of a view this is giving. Yeah, it's unlikely that you will see all of it. So the best way to understand is like sun 0 degree, almost 90 degree. So it's huge. It's observing in terms of mathematical detail. It's a 2 astronomical unit basically. So this point is the sun. So that disk is 2 astronomical units. It's wide. Now, yeah, it does not have full coverage, but it has more than enough coverage. And each exposure is 8 minutes long. Again, low Earth orbit is kind of fast. So it's like, 8 minutes, 8 minutes, they keep doing it like this. So they are doing this. And they originally wanted to try some other things, basically, how everybody thinks. What if we put it somewhere else? What if we put in Lagrange point? What if we put it in much further away, or things of this nature? All of them ended up costing a lot. So given the constraint and low budget requirement, they are like, okay, what is the best we can do? Well, the best is you do not build it. You just buy it. So to do that, they went into this topology of 3+1, meaning they're going to have 3 of them observing the wide fields, and they're going to have the center one observing the sun itself with overlapping field of view. Now, the primary reason why you have to have that center one, not just like 3 overlapping one, is because the dynamic range is too bonkers. Basically, you are talking about electron in free space. And you were like, yeah, that would be very dim. Yeah, it's very dim. It's impossible to see. And again, I would urge you to watch the video. It's like when he explains how the heck he removed it mathematically, all the things to see the glow of the electron, because the electron is not light emitting, but you have stars that are light emitting. So how the hell you see something that is much fainter? Well, you remove the motions of stars. It's amazing mathematics. Basically, if you understand that mathematics, you understand how the heck we have MRI that can see inside your body. So similar mathematics, they utilize that. So to see this, and dynamic range requirement, basically how sun at like 0 degree, it's too bright. It's super duper bright. If you have that falling onto your sensor, yeah, your sensor is bye-bye. So they have a specific telescope with basically sunglass that is looking at it directly, and is giving wide enough field, enough dynamic range where it's like, okay, I give some idea, but outside I cannot. Even if you made it ultra wide angle, it will be like overexposed. So they're like, okay, only this far. This inner ring is that sunglasses, and then you have wide one, which is much higher dynamic range, which is like tailor-made for fainter objects. So basically from almost 3 degrees to 90 degree. So dynamic range kind of made it important. We have to have this, otherwise it's not. And another benefit of that, if this is done correctly, it allows them to stitch all the data correctly, because they will have a central reference point. So that's the whole point. Narrow field imager, it's basically looking at the sun. And then you have WFI, wide field imager, and this will look from few degrees, basically like 3 to 4-ish degrees to 90 degree from Earth's point of view, if you are looking from Earth's point of view. And all of them are sun synchronous. But here's the deal, to achieve this sort of flower petal design, they must have equidistance between them. Like the geometry between them has to be kind of sort of precise. And each of this exposure is 8 minutes long. So field of view is the critical part. We have the technology, we have the sensor, we have observatories doing this. It's just that none of them have this huge field of view and tailor-made to observe electron flowing through a void of space. Basically, the idea is they want to understand how the heck electron goes from something that is magnetically propelled to something acting like a liquid. There is a transition that happens. And now again, we have some idea of it, but we do not have the whole picture. Basically, we are looking way too close. We need to zoom out. So the instruments about this, now everything about this project is off the shelf. That was the another reason why they chose for low Earth orbit, because low Earth orbit has seen an explosion of cheap products. So basically right now, if you want to make something for low Earth orbit, you have to pick up a call, and everybody on the other side will ask you only 2 things: how much, how many kilowatts, basically what is the weight of it, and how many kilowatts you need. Everything else is like yeah, we have this bus that will fit you. So that's why these both satellites looks inherently the same. They are the same bus, so to say. It's like take it and go. We have this sort of kilowatts capacity, we have this sort of kilogram capacity, take it and go. So that's how they made sure the cost is very low. Another aspect, again, that's why the propellant is water rather than some hydrogen, which again would have helped in a lot, but also would have increased the cost. So something like that. And again, torque rods. These are uniquely suited for low Earth orbit, because at that point in time, you do have enough magnetic oomph from Earth's magnetic field that you can react against it. So you have something like this. So one electromagnet, another electromagnet, another electromagnet. And based on current you are dumping into them, you can align yourself. Again, it's not like huge torque. That's why we do not use it for an International Space Station. But for something like this sort of lightweight puppies, more than good enough. And you do have reaction wheel where if those are not working or counteracting what you want to do, they can take care of that. And the most amazing part of it, hilariously, the solar telescope is a normal thing. We have a lot of solar telescopes like that. So you can see it has like the optical, what you call, the occlusion disk. So they have the occlusion disk, and then you have some there, and then there is a disk of polarizer. And that's normal. That's like, 15, 16 satellites have that. That's like take it and go. But this is the interesting part. First, they had to make sure that it's cheap. Second, they had to make sure baffles are very uniquely designed. Now, like, okay, why do you need baffles in space? Well, you do not need baffles in space if you are observing things like stars and all that. But if you want to observe electron cloud, you have to make sure that basically light going in a vacuum medium behaves more like a wave. So if it's going through a hard edge, it behaves differently. So they needed a baffle that can absorb all of it, not 1%, not 2%, order of magnitude of it. Basically, way too many zeros. I'm not gonna even count how many zeros they were talking about. Too many zeros. They want to make sure that sun is here, and my sensor from here starts to work, and it's like sun does not matter. Which again, if you know about anything about long exposures or anything about dynamic range, like that's almost impossible. That's why this has such a weird baffle. And again, to test the baffle, they had to do that testing in vacuum, because again, that scattering of atmosphere will defeat the purpose of it here. It only works in space. So that's why it has such a weird structure, like surprisingly good geometry. To achieve like this baffle takes care of the main sun, and then another baffle, another baffle, another baffle. So a lot of things, and it's very angled like this. It's like a pan. So they have this, and that's the most engineered part of it. What about the sensor? It's normal 2K sensors used in almost all missions. Like you look into Nancy Gray telescope, they have 2K square sensors. Those are already used in almost all system. Again, they wanted to make sure that is cool. How do they make it cool? They just have a heat pipe to a radiator. Again, it's not JWST, so money is tight. So they're like, bro, heat pump, go. So that's how it is. And field of view, that's the whole point. The point of view from these point of view, and again, not one, but all combined, is the reason why everybody is excited. But here's the deal. This cannot give you an image that is useful. It has the data in that image. It's just not useful. It requires bonkers amount of basically ground-based processing. It was another benefit of going to basically low Earth orbit. The data dumps from low Earth orbit to ground station is much easier. So you have to take the data and basically mathematically remove everything without throwing away the actual data, because there is some faint signal about electron cloud. So basically they have this much dynamic range, they throw away like almost 99% of it. Then they expand that 99%, then throw away that 99%. Then in that small thing you have the, okay, we can see. And like, what the hell? Yeah, that's how, that's why I said like the most amazing part of it is like somebody's like, hey, we have the tools, we have the mathematics. What if we combine both of them? It's like, think about it this way, like how the heck a MRI can figure out what's inside your body without even light or X-ray? It's just like your radio waves. It's like, what the hell? Fourier transform. So it has amazing Fourier transform that will be done on ground. And if you are smart enough, you can download all the images are publicly available, as in like the raw data. If you want to process, go YOLO on it. Now, the reason why I'm so excited about this could be book. Again, I cannot be definitely sure, but this could be big. Because again, right now our satellites to our power grids, they are very based on luck right now. Basically, if sun is good, we good. If sun sneezes wrongly, we dead. So right now we are just on the mercy of solar wind. That's not desirable. Now, like, don't we have satellites that are observing it? Yeah, they are not early enough, so to say. Right now we are like, okay, we have a buoy. If it starts to shake, tsunami is coming. That's not good enough. That's why we need to understand what the hell is going on. And early warning system needs very high precision, so to say. And again, price wise, again, 160 million for something like that, which has some probability of actually unlocking the secrets. Shut up, take money. And we must understand the whole process. Again, that's why that electron sphere is so important. It's like, how the heck magnetic field is going from magnetic to liquid domain? How the heck that's happening? And again, the mass that is ejecting, that's not that much, like compared to even like there are lakes on Earth that has more water than that. So it's not massive, but we are going through it. And in terms of charge particle, this puppy is charged. So we need to understand the whole scope, basically from early warning to prediction. There is a system. You have early warning systems where it's like, a buoy in the ocean that starts to bobbing down the run. That sort of is early warning. To prediction, where it's like, no, we can predict you long ago. Like basically how Japan went for a lot of research and development. They started to understand there are two waves in earthquakes. So you can have one wave that comes very early. If you can detect it, you can get almost 2 minutes early warning system for earthquake. They deploy it all around, and that's how they can make sure that all high-speed trains comes emergency brake. Basically, the detected emergency brake is already applied. Basically, train would be either slowing down to almost zero, or it would be at zero at moment of earthquake. So same way, we have to understand all the dynamics that is going on. Only then we can understand how the heck this is working. And our early warning system would be far more precise and predictive. It's not just like it is happening. It will be like, oh, it's going to happen from this point onwards. And there is another, the polarization is also helping us to see in 3 dimensions, that you have X and Y coordinate. Cool, awesome. Polarization, ironically, because again, we have such a magnetic domain interaction, that also gives you another data, is like how it's in Z dimension. So with 2D sensor, you're getting 3D data. Compilation of that data could reveal some awesome things. On principle, on mathematics, we right now we have like, okay, lower chronosphere, solar chronosphere, and then you have inner heliosphere, outer heliosphere. All of these have very blurry data points and all that. But this does work, but it's a very small thing. Basically, you're taking cup and scanning the ocean. It's like there is no whales in it. It's like, bruh, you gotta zoom out a bit. So that's why we want to do this. And if done correctly, if we figure out how the heck physics is at play, we know some idea of it. We just can see the whole picture without, giant black bars in between. It would be awesome. It's like, and the target mission is 2 years, and they are very clear on that. Inherently, if something bad does not happen, they should last for 4 years without too much issue. So basically, it's a money problem. If the 2 years mark, everybody is happy with it, they might get cancelled. If everybody is happy with it, and they're like, you know what, it's worth continuing. If they get paid, they can work for 4 years. So data would help a lot. Right now, we are like very narrow slice. We need the whole picture. Basically, from Sun's point of view, we are at low Earth orbit right now. We need to go to geostationary. So this could be big. Like this could be a small thing that is like, oh, it will have a huge effect. Or even NORAD is interested into them, and a lot of government agencies like, could you help us have this data coming to us? Very high response, basically low latency, so to say. They're like, yeah, we can do it. It's just not built for that. But again, anything is better than nothing. And again, if we figure out how the algorithm, how the hexagon is working, it would be awesome. So this was my presentation on basically NASA's Punch. Hopefully you have liked it, learned from it. In that case, please click the like button, share it amongst your friends. That will help me a lot. If you didn't like it, didn't enjoy it, I urge you to press dislike, press it twice to show me extra disappointment. Please leave a comment because I do try to reply to all of them. Subscribe, press the bell icon if you're free, and as always, thanks for watching.